Hey folks, my name's Nathan Johnston, and I want to talk to you about the Putnam competition, which happened just a couple days ago. And in particular, I want to go through the very first problem on that competition. So problem A1 on the 2024 Putnam. Now, this problem says determine all positive integers n for which there exist positive integers a, b, and c, satisfying 2 times a to the n plus 3 times b to the n equals 4 times c to the n, okay? So for problems like this, where you're looking for integer solutions or trying to determine when integer solutions exist, sort of your bread and butter first thing that you want to try is modular arithmetic, okay? But even before we do that, I want to try just playing around with small values of n, okay? I'm going to try like n equals 1, n equals 2, n equals 3, and see if I can find any solutions by hand to maybe just help me notice some patterns or something like that. When I try this, for example, for n equals 1, then that equation, it simplifies down kind of nicely. It just turns into 2a plus 3b equals 4c. And the question is, are there any integer solutions? Are there any integer values of a, b, and c that make this true? And just fumbling around a little bit, you're going to find some solutions just by eyeballing it very quickly. For example, if a equals 1, okay, then I want to choose b that makes that whole left-hand side a multiple of 4. And well, I can just choose b equals 2 to make that happen. So that I've got 2 plus 6 equals a multiple of 4. C is 2. So I've got 8 on both the left and right hand sides. Okay, so yeah, there is a solution for n equals 1, and you can find that very quickly just by eyeballing and playing around with things. And then maybe you try this for other values of n equals 2, n equals 3, and you're going to be less successful. You're not going to find any solutions just by eyeballing it in those cases. And I mean, that doesn't necessarily mean that there are no solutions, but it does mean that now we've got to whip out our mathematical bag of tricks and try to figure out what's going on when n is bigger than or equal to 2. So first thing we're going to try, modular arithmetic. Let's see if we can find some values of n for which there are no solutions. I don't have any great insights at this point. Let's maybe just try small moduli, okay? So let's start off with mod 2, okay? Like consider when both sides are even versus when both sides are odd, okay? So if we just slap a mod 2 on both sides of the equation, well, the 2a to the n term, that's always even, and the 4c to the n term, that's always even, so those just become 0 mod 2, and we're just left with the 3b to the power n. That's got to be even. It's got to be 0 mod 2. And the upshot of that is that, b has to be even. Okay, and that's all we can get out of mod 2. Okay, so now let's move on to another modulus. Okay, maybe you try mod 3. Okay, mod 3 is tricky, actually. Very naturally, like you probably would try mod 3 next. I tried mod 3 next, but it's a little bit tricky at this point to work through all the cases and exactly what it tells us. Okay, so instead, I'm going to skip over that. I'm going to go on to, well, what does mod 4 tell us? Okay, so if I work mod 4 on both the left and right-hand side, then what happens is, okay, the 4c to the n, certainly that becomes 0 mod 4, because that's always multiple of 4. But also the 3b to the n becomes 0 mod 4, right? Because remember, we just learned that b has to be even, okay? And we also know that we only care about n bigger than or equal to 2, right? Because we already know the answer when n equals 1. There are solutions. So n bigger than or equal to 2 for all of what we're doing now, okay? So we've got an even number at least squared. That's a multiple of 4. So the 3b to the power n term, that's 0 mod 4 as well. We're just left with 2 times a to the power n. And what that tells you is, well, that's got to be a multiple of 4, so a's got to be even as well. Okay, and now the gears start turning in our heads. Okay, wait, we just learned that a's got to be even. We already knew that b's got to be even. So now, like, what jumps out at me? Like, what I think my approach is now is, well, it would be wonderful if I could show that C is also even, then we're going to be done, okay? That would show that actually there are no solutions. And why is that? Well, okay, the idea is that if all of A, B, and C have a common factor in them, 2 in this case, because they're all even, well, then you could find a smaller solution that gets rid of that common 2, right? Because like in this equation here, this 2 times a to the power n plus 3 times b to the power n equals 4 times c to the power n. Sort of if there's a global scaling affecting those a, b, and c, you can pull it out and the equation's still going to be true. Okay, in particular, in this case, like each of a, b, and c, if they're multiples of 2, I could pull out that 2 to the power n from the left-hand side and the right-hand side, and now I've got a smaller a, b, and c that also satisfies that equation. And then I could just repeat this, okay? Maybe they're all still even. I pull out another factor of 2. Maybe they're all still even. I pull out another factor of 2. But eventually, right, because these are positive integers, there are only so far that you can reduce things down to. And eventually you must run out of 2's to pull out. But if we show that A, B, and C have to be even, then we get a contradiction. We get like these two ideas that don't work at the same time. it all must be nonsense. There must be no solutions at all. Another way to think about this is like, maybe I phrase this like at the very start of my argument here as, I'm not just looking for any solution A, B, and C that works. I'm looking for the smallest one. Okay, and now via my argument that I'm going through here, A, B, and C all have to be even. Therefore, it's not the smallest solution, because I could, get rid of that common factor of 2 in all of them and get a smaller solution. So again, like, I get a contradiction. Okay, so that sort of clarifies a path for us here. Our goal is now to show that C is even, and so far I've worked mod 2 and mod 4. Maybe let's just go up to mod 8, okay? Like, I'm trying to figure out things about powers of 2 in the A, B's, and C's. Let's go up to the next power of 2 modulus, okay? So let's work mod 8, and then on the left-hand side, I've got 2 times a to the power n. Well, okay, so there's 1 2 in that from the 2 that's out in front of a to the power n. And then there's at least 2 more 2's in that, right? Because a is even, and again, n is bigger than or equal to 2. So that term, 2 times a to the power n, that's at least a multiple of 8. So mod 8, it's congruent to 0. So it goes away. We're just left with a 3 times b to the n is congruent to 4 times c to the n. Now, we're a little bit stuck here, but if n is bigger than or equal to 3, then we're done, okay? Because on the left-hand side there, if n is bigger than or equal to 3, b to the power n is a multiple of 8, because b, remember, b we already showed is even. So if I'm raising that to the third power, now it's a multiple of 8, 2 cubed. Okay, so then the left-hand side, mod 8 would be 0. So the right-hand side must be as well, which would show that c is even. Okay, so if n is bigger than or equal to 3, great, we're done. We've just shown that there are no solutions. Okay, so there is a solution when n equals 1. There are no solutions when n is bigger than or equal to 3. The last man standing is n equals 2. Are there any solutions there? And we still have the facts that a and b are even to work with. So let's make use of those, but let's go to other moduli now. Let's go back. Remember how I skipped over mod 3 back in the day? Well, let's try to work mod 3 now, specifically for the n equals 2 case. Okay, so apply mod 3 to both sides of this equation here, and of course the 3b squared term goes away, and you're left with 2a squared equals 4c squared. Okay, now, this equality here, okay, go through the different cases, okay? For example, if a is 0 mod 3, so if a is a multiple of 3, then the left-hand side, that's 0. Okay, if a is 1 mod 3, it's 1 larger than a multiple of 3, then the left-hand side is 2 mod 3. And if a is 2 mod 3, then squared, it becomes 1 mod 3 times 2. The left-hand side is still 2 mod 3. So the left-hand side is always 0 or 2 or 2. And a similar argument shows that the right-hand side is always 0 or 1 or 1. So the only way that you get equality here is if, well, on the left-hand side, if that's a multiple of 3, right, if it's 0 mod 3, and also if the right-hand side is 0 mod 3, if it's also a multiple of 3. Okay, so a and c both have to be multiples of 3. So I'm going to say a is, 3 times k for some positive integer k, and c is 3 times l for, again, some positive integer k. And then I'm going to plug that crap in. Okay, and what I get then is I get this new equation, 6k squared plus b squared equals 12l squared, after I simplify things down and cancel out one common factor of 3 across the entire equation here. Okay, and I'm just going to repeat this logic. Okay, I'm going to work mod 3 again. Okay, if I work mod 3, the 6k squared goes away, the 12l squared goes away. I'm just left with b squared is congruent to 0, so b's also got to be a multiple of 3. Okay, so I've just showed that each of A, B, and C, they're all multiples of 3, and now we do a similar argument to before, okay? If they're all multiples of 3, then this can't possibly be a minimal solution, because you could just get rid of that multiple of 3 from all of them, and you get a smaller solution, and you keep on whittling down, and, eventually you're going to get a contradiction, right? Like, you can't have a minimal solution where all of them are multiples of 3, so, there just is no solution whatsoever. Okay, so yeah, our conclusion is, well, no, there's no solutions when n equals 2 either. Okay, and then we're just done. Our conclusion is that, yeah, there exist positive integers a, b, and c satisfying 2a to the n plus 3b to the n equals 4c to the n if and only if n equals 1. Okay, that's all I got for you. Thanks for watching, everyone. I'll see you next time.